Hello, 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 everybody. Welcome to Math this Tuesday, December, what is this, the 8th? This school year is just something else, isn't it? It's already December. Time is moving very slowly and very quickly, all at the same time. Incredible. Thank you for being here. Today, we're taking a look at the numerical pattern work that we did yesterday, and we're thinking about it in terms of some real life situations, because there are going to be a number of times as someone who uses math more than they think, I use math more than I really think about. There will be plenty of times in your life where you will need this sort of numerical pattern knowledge in order to, calculate how much something is going to cost, or calculate, if you ever want to like print t-shirts or make CDs, or, using these kind of numerical patterns to give yourself a bigger idea and be able to calculate unknown quantities quickly by using those patterns. That's what you'll need. There's your I cans. I can define numeric pattern, and I can write an expression that shows a numeric pattern. And I was noticing something is yesterday, up there, it didn't say numerical patterns in real life situations. It said intro to numeric patterns. And then down here, it says numeric patterns. So I was like, as I'm using them, I'm kind of thinking, well, is it numeric or is it numerical? And I looked it up, and it's kind of interchangeable. Both words mean kind of or relating to numbers. Okay, numerical is, according to the internet, numerical is more about the usage of numbers and how numbers are being used, like in a numerical pattern, right? But for all intents and purposes, both words kind of are interchangeable, so we can use numeric or numerical, and it kind of works for both. In fact, I even was reading on the internet that there's a difference between British English and American English, where American English tends to use more numeric and British English tends to use more numerical, which I thought was interesting. In Britain, they don't call it math class either. They call it maths, like mathematics. They shorten to maths with the S on the end of it, while we just call it math. There's your fun vocabulary lesson for the day. Now let's get into the actual maths part. So when we're thinking about, see, there it is again, numeric patterns, okay? We really want to think about this idea of putting it into context. Yesterday we talked about numeric patterns. Hold on, let me pull the word wall up. There it is. Yesterday we talked about numeric patterns being down there at the bottom. There it is. Being a sequence of patterns, a sequence of numbers that share a relationship, right? We're adding the sort of same amount, or we're multiplying by the same amount every time as we go step to step, sort of our corresponding or sequential numbers there, okay? And we will see this a lot because, in life and in real world situations, these patterns tend to come up because, we are a society that kind of thrives and works on patterns. And it makes us easier to process things rather than just like a random assortment of things. So the first one I want to talk about, I'm going to move the word wall away for now, is this pattern here. We're going to talk about the skate shop. I got my skateboard here. I was working on it for Grovember. I can do many things on it that I could not do a month ago, which is great. But let's imagine we're purchasing some skateboards, and let's say we're starting a skate club at school. Okay, and the skateboards we're going to buy don't come assembled, so we need to put them together ourselves. So we need to think about, okay, how many skateboards are we going to buy, and so how many wheels are we going to need to get to make sure that all the skateboards have wheels? Okay, so we can use a data table, kind of like the ones we had yesterday. So we're thinking about number of skateboards on the top, and then number of wheels on the bottom. And because it's a pattern, skateboards have how many wheels? 1, 2, 3, 4. Most often. You will see the occasional skateboard that has more or less than 4 wheels if it's like a special thing. There's like videos on YouTube of like, we rode a skateboard that had 24 wheels on it. It's kind of interesting. But almost all skateboards you're going to see have 4 wheels. So the number of skateboards on top is going to correspond with the number of wheels on the bottom. They're going to be connected. And let's start, before we even start with 1, let's start with 0. If we were to purchase 0 skateboards, or if we were to put together 0 skateboards, how many wheels would we need? Exactly, 0, right? The wheels don't do us a whole lot of good without the board to go with it, okay? Let's say we've got our 1 skateboard here. 1 skateboard. How many wheels are on that skateboard? 4, okay? And then the numbers are going to correspond from there. So 2 skateboards. How many wheels? 3 skateboards. 4 skateboards. How many wheels? Okay? And then what we want to do is we want to try putting that or explaining that in words or as a mathematical expression or a number sentence without an equal sign. Right? So being able to say, okay, so how could we explain this and say for every skateboard, let's figure out an expression that can show for any number of skateboards we wanted to buy, how many wheels would we need? I see an 8 in the chat for our 2 skateboards. 8 wheels, yep, 4 plus 4, right? Then from there, 8 plus 4, 12. 12 plus 4, 16, okay? And then so on and so forth. 5 skateboards would be 20 wheels, 6 skateboards would be 24 wheels, and so on, okay? Now let's think about an expression for this. If we had our 0, right, that's our kind of starting point. We had 0, and do we really even have to put anything because it's a 0? No, we'll just use 0, right? 4, right, we had our start plus 4. 4. 1 group of 4. We could even say 4 times 1. Right? 8 would be how many sets of 4? 2, right? 2 skateboards, 4 sets in each, 4 wheels on each skateboard makes 8. This one, 4 times 3, and then 4 times 4, right? Okay, so there's our pattern. There's our expression, right? For each skateboard, we need 4 wheels, okay? So I already see, ooh, nice expression in the chat there. I see n times 4 would show this pattern. Do we agree? I agree. Does it have to be n? No, could be any variable we want. Could be, you know, S. We could make it an S for skateboard, right? We could make it a B for board. We could make it an X for extreme. We could do a great number of things, any variable, but the key point here is however many skateboards you have, you multiply it by 4 to get the number of wheels. So if I asked you, how many wheels would we need if we had, or if we wanted to buy 12 skateboards for our skate club? How many wheels would we need? Substitute in your 12 for your variable, and then multiply. 12 times 4 is? Okay, drop it in the chat. Let's go to our digital whiteboard here and take a look at a couple other examples. Okay, this one here, we're at a restaurant. Okay, the top pattern shows the number of tables in our restaurant, and then below it shows the number of seats in our restaurant. Okay, so what type of expression or what type of, you can use words too and be able to say, like we said on the skateboard one, you know, for every skateboard, you need 4 wheels. right? That's another version of saying our equation of S for skateboard times 4, right? So what would we say for this one? Taking a look at these two corresponding patterns here. One table has 6 seats, 2 tables, 12 seats, 3 tables, 18 seats, 4 tables, 24 seats. Give it another minute. I see an answer in the chat, but I'm interested to see if we agree with that answer that's in the chat. Yeah, right? Noticing that correlation of for each one of these, how do we get from 6 to 12? What's the relationship? We're adding 6. How do we get from 12 to 18? We're adding 6. 18 to 24, same thing. So plus 6 every time. So that means a new group of 6 comes in every time we add a new table, right? 6 seats for every table. Okay, that's the way to say it in words. In an expression, I saw somebody say z as their variable times 6. So for every table, if we had z equals 1, z equals the number of tables. It is important to kind of label what your variable is so we know, right? If z equals the number of tables, then to find out the number of seats, you do z times 6. So if we had, again, 12 tables in our restaurant, how many seats would we need? Right? Substitute in the 12 for that z because we're trying to find out 12 tables, and then simplify and use multiplication. Makes sense? Let's try one more. I'm going to make it a little more challenging. This one's going to be about, hold on, let me move it. Ta-da. This one's going to be about socks. And I wrote socks all messy, but this one's going to be about socks. Let's imagine that we're buying some socks for, I don't know, how about a soccer team? Okay, and we're buying socks by the pack, right? And each kid gets a pack of socks. We're just going to buy them all as a group. And take a look at this pattern. What do we notice about this particular pattern? This is our kind of price list for these packs of socks. Take a look at this one. Notice the interval between consecutive numbers of our pattern. This one's a little bit trickier. So if we're stumped, again, I'll give you a little help here. What is the interval between, or what's the difference between each step in our data table? Right? What's the difference between the price of 1 pack of socks and 2 packs of socks? What's the difference between the price of 2 packs of socks and 3 packs of socks? Okay, we're starting to get it here. Yeah, I'm seeing +5, +5, plus 5. So we know our interval is going to be 5. But I think what's stumping some people is take a look at that first pack of socks. How much does it cost? Does it cost $5? So we see an idea here of P as our pack of socks times 5, where P equals number of packs of socks. Now let's try that and see if that works. So if we had one pack of socks, we substitute a 1. Well, if we substitute a 1 for the P for one pack of socks, then we end up with 1 times 5. Interesting. Because what would we need? This one's tricky. So what do you want? What do you think we should try? Because yeah, the P times 5 just by itself doesn't quite work. We know we need P times 5. We need times 5 somewhere, right? Because we're adding a group of 5. But then what are we going to do to our expression to make it so our variable lines up? So it's to start with 2 times 5 with 1 instead. So we've got, here's an idea. In the chat, we've got P times 5 plus 5. Let's see if that works. So if P equals the number of packs of socks, we plug in the 1 times 5 plus 5. That equals 10. For 2 times 5 is 10. Plus 5 is 15. Sure. For 3 times 5 is 15. Plus 5 is 20. That works. Would you agree? So this could be an expression that would fit. P times 5 plus 5. Nice. I like it. The other thing you could try is this. Because, and it was Ava's comment in the chat that says start with 2 times 5 with 1 instead. So that made me think. If we want our variable to be 1 more than the number of packs of socks, what if we did something like this? P plus 1 times 5. Try plugging in some your 1, your 2, your 3, and your 4, and see if that works as well. So if we put a 1 there, 1 plus 1 times 5. Does that work? Plug your 2 in for the packs of socks. 2 plus 1 times 5. Does that work? Yeah, it does. Right? And why it works is because, right, if you're adding 1 before you multiply it, essentially you're adding a group of 5. right? Because if you're adding 1 to whatever it is and then multiplying that by 5, you've added essentially one extra group of 5. It's the same as p times 5 plus 1 times 5, which, oh, look at that. That's the exact same thing as our first equation. Or our first expression, excuse me, not an equation. Yeah. So 2 different ways to say that, but the idea being we had to do a little bit of kind of trickiness to make sure we can find an expression that fits this pattern. And nice work, those of you in the comments working it out. Okay, and even if I don't see you in the chat, thank you for being here, and I appreciate you working on all of this. So the exit tickets today is going to be similar stuff. It's going to give you a data table like this one or like the other ones that we saw on the digital whiteboard. If there are blank spots, fill them in based on the pattern. You can use words or a mathematical expression to describe what's going on in these patterns, and then it's going to give you a little bit of it's got a kind of an extra question, an additional question connected to each set of data. All right, everybody. Thank you for tuning in. Office hours will be open promptly at 11 o'clock. If you have questions, good luck. Try it on your own. Don't be afraid to struggle, because you can do it. And then if you have questions or you want extra practice, come see me in office hours. Thanks, everybody. Take care.